I'm going to talk about identification and estimation of dynamic discrete choice models. I will start with the model, with the structure of empirical dynamic games, or the class of empirical dynamic games that are used in most empirical applications. I will go quickly through this because you have already seen many presentations on this, but basically it's to present notation. Then time is discrete and indexed by t. I'm going to consider the discrete time all the time, though there is a recent and growing literature with papers by Peter Arcidiacono and Jason Blevins on estimation of this type of dynamic games in continuous time, and it's a growing, a very interesting literature. I'm going to focus on discrete time models. The game is played by n firms. I'm going to talk about firms. You can think players more generally. Indexed by I, and they make decisions every period to maximize an intertemporal payoff function. Delta I is the discount factor of individual I. Pi I is the payoff function, the period payoff function of firm I at period t. Every period, they make an investment decision. I'm going to represent A as this investment decision, and I'm going to consider that A belongs to a finite set of possible choices. Okay? Okay. The payoff function, we are in a game. Then the payoff function at period t depends on the own action, AI, but also on the actions of the other players in the game. Xt is the vector of state variables. We have endogenous state variables that evolve according to a Markov process that depend on the choice of the individual. And X contains also, or may contain at least, exogenous state variables that follow Markov process that do not depend on the action of the players. Okay? Example of this, for instance, is the Peikes and Maguire model of competition in product quality. Here, the endogenous variable is the level of quality of the product of an individual. There may be exogenous variables set that affect basically the demand or the marginal cost of the fixed cost of the firms. Inside the one period profit function, we can have a model of price competition that determines the variable profit that I represent here by R. Then we can think R as the result of a Bertrand-Nash equilibrium, given the products that we have in the market and the levels of quality firms compete in prices. There is a Bertrand-Nash equilibrium in prices, and that determines this variable profit Ri. In addition to the variable profit, we can have an investment cost, or we have an investment cost that depends on the amount of investment on quality of the firm and also the installed quality. It might be more costly to improve the quality of your product if you are in a high level of quality than if you are in a low level of quality. And the stock of quality can evolve according to this very simple rule. And in this case, there may be both positive investments in quality and negative. There may be disinvestments in quality. Okay? As I mentioned, the endogenous exogenous state variables follow an exogenous Markov process. There are many different ways in which the endogenous state variables may evolve depending on the application. We can have deterministic transitions. We can have stochastic transitions. Putting together endogenous and exogenous state variables, we can represent the transition rule of the state variables, of the whole vector of state variables, according to this control first order Markov process. Okay? Okay, then this is the setting. This is the type of models that we are going to study and try to estimate. Almost all the empirical applications, especially in I/O of dynamic games, they have concentrated, or they have assumed Markov perfect equilibrium. Then let me introduce this equilibrium concept briefly. But let me start with a more general type of equilibrium concept. And let me suppose that players' strategies depend on the information set that a player has at period t. Okay? Then let calibrographic I subindex t represent the information that firms have in this market, and let me consider that this is a complete, for the moment, it's a complete information game where everybody has the same information and everybody knows everything about demand and the cost of everybody. And there is no heterogeneity in the information set IT. And alpha j I is just the strategy function of a player. Given the information that I have at period t, I behave according to this alpha j I. Okay? In principle, this information set includes the current values of the state variable, xt, and the whole previous history of decisions of all the players and state variables of all the players. Okay? Then, given this, okay, definition of what is IT, we can, and given a strategy function for my competitors, okay, I can define a transition probability of, this would be I, well, this is X, okay? Then I can define a transition probability of I, of the information set, taking into account this primitive of the model, okay? Okay? Then given this transition probability of the information set, I can define a Bellman equation, a single agent Bellman equation. I index in the value function by alpha. That means that if everybody behaves according to the strategy functions in alpha, V alpha is the value that individual I gets at period t, behaving optimally at period t. Okay? And this is a Bellman equation that is going to give us the value function. The solution of this Bellman equation is a single agent Bellman equation once I fix the behavior of my competitor. And I can define, well, the solution of this Bellman equation give us the best response of a player. Taking as given the strategies of the other players, I can obtain what is my best strategy function. And it's a function because it's a best response at every possible value of the information set. Okay? Then we can define an as equilibrium in this model. An as equilibrium is just a set of equilibrium strategies where everybody is best responding to everybody. Okay? And this defines a very general class of equilibria. Okay? Then in this context, what is a Markov perfect equilibrium? A Markov perfect equilibrium is a particular type of this type of equilibrium where we impose the restriction that players' strategies only depend on payoff relevant state variables. That is, the IT, basically the set of information that the agent conditions to construct their strategy are only variables that have an effect on today's profit and future profits. Okay? This, of course, reduces very substantially the dimension of the state space, the dimension of our value functions, and our strategy functions, and is very convenient. And that's one of the, if not the main reason, of course, reduces the type of equilibria, the number of equilibria that we can have in the dynamic games. Then reducing the dimensionality is one of the main reasons why the literature has considered this equilibrium concept, initially proposed by Maskin and Tirol. There is this equilibrium concept is not arbitrary. It has some interesting property, is that suppose that I know that all the firms, I'm a player in this game, and I know that all the other players behave according to this type of Markov strategy that only depend on the state, on payoff relevant state variables at period t. Then there is not any improvement from deviating from using more information. Okay? Under this type of equilibrium, basically, using only payoff relevant state variable is, if you want, an equilibrium of a metagame where we could endogenize the amount of information that firms use, okay? There are not incentives to use additional information to condition my behavior on non-payoff relevant state variables if I know that the other players are using only payoff relevant state variables. This is not the case if I know that my competitors are using strategies that depend on less information than the payoff relevant. Then I can obtain gains by using basically my payoff relevant state variable. And there is this idea of best responding in terms of how much information we should use in the concept of Markov perfect equilibrium. Okay? Yep.
This doesn't rule out all kinds of trigger strategies, right? But it rules out some.
It rules definitely, and that's the key restriction. Does it mean that we could not have, in the case of firms competition, some kind of cooperation between firms? No, we can have equilibrium that look like very much like the type of equilibrium if firms are colluding. But definitely we are going to eliminate some type of equilibria with trigger strategies.
But a simple type of trigger strategy where we have a cartel that triggers into myopia, something like that, that's still a Markov, right?
That's still a Markov equilibrium. Exactly. Good, very good point. Yeah. Yep, of course, it's not without restrictions. Okay. Okay, then, given a vector of players' strategies, a vector alpha with the strategy functions of all the players that depend only on payoff relevant state variables, I can define this profit function that now only depends on my action because I have solved here the strategies of the competitors. And I can define this transition probability of state variables that explicitly only depend on my own action, because I have solved here the action of the competitors according to their strategies. And once I have this profit function and this transition probability of the state variables, what I have is just a single agent dynamic decision problem, okay? And the value function, V alpha, is the unique solution to this dynamic programming problem, okay? And taking as given the strategies of the others, okay, I have a well-defined dynamic, single agent dynamic decision problem for each player that is going to give us, again, the best response, the best reply strategy for a player I. And a Markov perfect equilibrium, again, is a set of strategies where everybody is best responding to everybody. Okay? Okay, equilibrium existence. Well, Doroselsky and Satterwhite, in a paper in RAND 2010, they showed that very simple examples where when we have that the action space, the decision space is discrete, it's not difficult to find examples where these models do not have an equilibrium, okay? This property, together with the fact that introducing IID private information shock is a very convenient type of an observable for doing econometrics, has motivated introducing, basically extending the model that I have presented that is purely complete information to a very simple type of incomplete information version of this model, okay? Where in addition to the vector of a state variable x, that is common knowledge to this firm, we consider that every period firms receive a private information shock that is IID across players and IID over time that can affect behavior, okay? Introducing this type of IID private information shock has, as shown by Doroselsky and Satterwhite, imply that we always have, for any configuration of the structural parameters, we have at least one equilibrium in this type of model. Then equilibrium existence is guaranteed. And in addition, it's going to give us a very convenient type of econometric error, okay, econometric unobservable, because basically it can rationalize why individuals make different choices when the observable state variables are the same, without generating endogeneity, okay? Without generating endogeneity in the sense that the actions of your competitors depend on their epsilons, but their epsilons are not correlated with your epsilon. And from an econometric point of view, there is no correlation between the actions of the competitors and the unobservable in my best response function, okay? And these are very convenient, not necessarily realistic, but very convenient type of econometric errors. And all these models typically they have this error. Of course, most of the applications incorporate other type of unobserved heterogeneity that is richer, okay? But we always have this type of econometric errors for equilibrium existence and for convenience in the econometric approach, okay? Then, basically, as I have mentioned, in addition to X, we incorporate these private information shocks that are IID across players and over time. And then something that is convenient is to, of course, because we can have as many epsilons as choice alternatives, and these are continuous variables, epsilons, we are increasing also the dimension of the state space substantially, and that in terms of computation can be challenging. Then it's going to be very convenient that, as we do in single agent models following the work by Ras and others, we saw that we can represent both the solution of these dynamic games and the estimation eventually of these dynamic games in terms of some description of the strategy functions that are integrated over the epsilon, okay? And that's what we are going to do. We are going to represent now a Markov perfect equilibrium, not in terms of the strategy functions alpha that depend on X and epsilon, but in terms of integrated strategy function, versions of alpha that are integrated over the distribution of epsilon, okay? And that's what we call conditional choice probabilities, okay? It's just Pi of AX is the probability that individual or player I, according to the strategy alpha, chooses alternative A, given that the vector of common knowledge state variables is equals to X, okay? And if the epsilons enter additively in our payoff function, we can apply a Hodge-Miller inversion theorem to show that basically there is a one-to-one relationship between choice probabilities and the strategy functions, basically, okay? Given strategy functions, of course, we can always integrate over the distribution of epsilon to obtain choice probabilities, but it's also true using Hodge-Miller is a corollary of Hodge-Miller inversion theorem that given choice probabilities and given that we know that epsilons are additive, we can always recover basically these strategy functions, unique strategy functions, which are consistent with these choice probabilities. And there is not any loss of information, again, given that epsilons are additively separable, in using this representation, probabilistic representation of the strategy functions instead of this, okay? And then, okay, similarly as I have done before with the alpha function, with the strategy functions, we can define also versions of the one-period payoff function and the transition probability of the state variables that use these choice probabilities. For instance, pi p is the expected value of the payoff function pi I, okay? integrate it over the actions of my competitor using the vector of choice probabilities of my competitors, P minus I. Okay? And that's the expression. Similarly, Fp is the transition probability of the state variables from the point of view of player I, taking as given the choice probabilities of the competitor. Okay? And therefore, is the integral of this primitive, okay? The Fx transition probability integrated over the actions of my competitors using their choice probabilities. Okay? And once we have done this, we have that the integrated value function, that is a value function integrated over the distribution of epsilon, is a solution to this type of Bellman equation. Again, taking as given the choice probabilities of the other, there is a unique vector, a unique value function that solves basically this Bellman equation. Notice that it's an integrated Bellman equation because we are integrating the max over the distribution of the unobserved heterogeneity. But as we know, these integrated Bellman equations have very similar properties as the actual Bellman equation. They are contractions. They have a unique fixed point. Okay? Taking as given the choice probabilities of the other. Okay? Sure. Good question. Okay, there is Harsanyi's theorem that probably you're familiar with that basically says both for the static and dynamic games, says that basically every equilibrium in mixed strategies in a model without private information can be interpreted as a Bayesian Nash equilibrium in a model with incomplete information. And this is one-to-one. Any equilibrium, Bayesian Nash equilibrium in a game of incomplete information can be interpreted as a equilibrium in mixed strategies in a game without incomplete information. Then that's the case here. And interpreting this result as an equilibrium in pure strategies in a game of incomplete information. But you could interpret it also as an equilibrium in mixed strategies in the model where we do not have the private information epsilons. Okay?
That's a little surprising. Like, so if I went back to your motivation where we're saying, suppose that we don't have a pure strategy equilibrium in the dynamic game, but there exists one in mixed strategies.
Yeah.
It's not obvious to me that the one, let's say it's unique, that the unique mixed strategy equilibrium would be the one that we would get with our particular G technology. So this G technology is dictating something about the pure strategies that we're then mixing into.
That's a very good point. Yeah, that's a very good point. Yeah, we are getting to stuff that I don't feel very comfortable in terms of theory. But let me make the following claim. Similarly, as we can have different distribution of the private information here, we could have equilibrium in mixed strategies where we have different type of mixing the strategies. It's not necessarily uniform mixing, but there may be different ways in which we can mix the pure strategies. No? And I think that this distribution of epsilon would correspond to the way that we do the mixing in the model with complete information, without private information. Yeah, very good point. Okay, then given that we have solved the dynamic programming problem of each player taking as given the choice probabilities of the others, we can define this best response choice probability function. And I have solved the dynamic programming problem. I have these conditional choice or choice-specific value functions. And then the probability of choosing an alternative A for player I is just the probability that this plus the corresponding epsilon is the largest value, okay? And that's basically what we have here. This expression in the right-hand side is the best response probability function of a player, okay? It's like the best response strategy, but in the space of choice probabilities, not in the space of actions, okay? A Markov perfect equilibrium in this model, of course, we have as many equations like this for every possible player, every possible action, and every possible value of x. And we have a large system of these best response equations. I have put everything together here, but you can see that these best response equations define a mapping from the space of choice probabilities into the space of choice probabilities. Then it's a fixed point mapping. Choice probabilities belong to the simplest. The function phi is continuous in these models as long as the distribution of epsilon has unlimited support and not massive probabilities. And then simply, you can see that by Brouwer's theorem, we have at least one equilibrium. Typically, we have multiple equilibria in this type of model. Okay? A particular example is when we have a particular and very common example in empirical applications, when epsilon, these additive epsilons, we have one for each choice alternative, and they are IAD extreme value type 1 distribution. In this case, the integrated Bellman equation has this logarithm of the sum expression, and the best response choice probabilities has this logit expression. Okay? Then you can think already in a way of in a method, in an algorithm to compute an equilibrium of this model. Let's start with an initial guess for the vector of choice probabilities. Given this initial guess, let's solve the dynamic programming problem of every player using this contraction mapping. We obtain the value function for each player. We plug it in here. We plug it in the choice probabilities. And this gives us new choice probabilities for every player, action, and x. We test for convergence. If there is no convergence, we come back with the new choice probabilities. We calculate these guys, and then we iterate in this fixed point problem, and so on. Okay? Then this will be a fixed point. Basically, this is the algorithm that I have described. It is just fixed point iterations here. Okay? It's a more detailed way of describing fixed point iterations. Okay? Then solution methods, I will go quickly through this because I'm going to focus on identification and estimation. But let me just describe this algorithm in a vector form. And suppose that x, the vector of a state variable, is discrete. And therefore, it can be described in terms of a finite set of possible values. Then we can, for every action of a player I and an action of the competitors, we can describe the vector of payoffs or the payoffs of a player, this capital pi I, as a vector with as many rows as possible values of x. Okay? Similarly, for every possible action of a player and the competitors, we can define a transition probability with dimension x times x for the state variables. We have also the discount factor and the distribution of epsilon. Okay? Then again, I can define this now integrated, given a vector of choice probabilities for all the players, I can define this vector of integrated or expected payoffs, and now this matrix x times x of transition probabilities that is integrated over the action of my competitors. Okay? And given that, then is quite straightforward using a vector programming the implementation of this fixed point algorithm, okay? Basically, this is a vector of value functions, okay? This is a matrix, this is a vector of payoffs. We can iterate, basically, to update the vector of value functions using this expression up to convergence, and there will be convergence because this is a contraction. And once we have this vector of values, we plug it in here, and then we get new choice probabilities, okay? And so on, okay? And very simple to implement. This particular fixed point algorithm always converge. What is the potential problem of this algorithm is that this equilibrium mapping phi is not a contraction. We have that every best response function of a player is a function, is well defined. The dynamic programming problem of a player taking as given the choice probabilities of the competitors is a contraction. But the equilibrium mapping, in general, in these models, is not a contraction, unless we impose additional and strong assumptions, okay? Then this algorithm, this fixed point algorithm, may or may not converge. Then alternative methods are Newton's method and also spectral residual methods, okay? Then this is, as I have mentioned, this is the fixed point iteration. Newton method is just looking at the equilibrium problem as a problem of solving a system of nonlinear equations in P, okay? Then we want to get a zero of this system of nonlinear equations, okay? And then we just apply Newton to solve this system of linear equations. What is the advantage of Newton? That almost always converge, has super strong convergence properties. In fact, quadratic fast convergence properties. What is the main computational problem of Newton? That we need to calculate the Jacobian, many times, the Jacobian matrix of this best response mapping. And that's a very complicated object, okay? Notice that what we need to do is to calculate the derivative of how the best response of a player changes in one particular action and state when we change the choice probability of other player in a particular action and state, okay? Then to get basically this derivative, we need to basically solve repeatedly many dynamic programming problems. Okay, and this is, and we need to do this for every possible player, action, and state. And calculating this Jacobian matrix is an extremely complex object, and we do not have closed forms of expressions for this, of course. Okay. You are going to use, for sure, implicit function differentiation. But despite that, basically, you are going to have, at the end, I mean, to invert a huge matrix. And it's challenging. Of course, you and Fedor can do everything. Yeah. Good question. We are talking about solution for the moment, not estimation, okay? Then basically what the game that we are playing here is that suppose that you know all the structural parameters. Suppose that you know the payoff function and the transition probability of the state variables, the discount factor, and the distribution of epsilon. Let's obtain an equilibrium of this game under this parametrization, okay? Then you are going to obtain it at every value of x. We are considering, of course, there are alternative ways of trying to approximate. I'm talking about an exact solution for every value of x, okay? you could consider, I'm not going to get a exact solution. I'm going to consider that P, the vector of choice probabilities, belong to a particular parametric family, for instance. And then I'm going to look for the vector of parameters in this family that solves a particular fixed point. We could do that. We will reduce very substantially the dimensionality of the problem, but we are getting an approximation, okay? And that can be very reasonable in many applications. But I'm talking about the exact solution of the equilibrium, not getting an approximation. Okay? You're welcome.
Just for, again, starting with the Doroselsky,
yep.
let's say that we don't have an equilibrium in pure strategies with no noise, with no private information. Now let me set this up, but subject to the variance of the private information being 0.
Yep.
So I'm back to the non-existence in pure strategies.
Yes, eventually you will get. You can consider here different versions of this model for different variants of epsilon and making these variants go to 0. Eventually, if you have a model that incomplete information doesn't have an equilibrium, they will disappear.
It won't exist here.
It will not exist here.
So in practice, when you do this, you will be looking at smoothing or the variance parameters in the CCP that has enough noise to give you the equilibrium.
Good question. Typically, we do not estimate the parameter the variance of epsilon because in discrete choice models is not identified, okay? And then everything is relative to the variance of epsilon. Then we do not have the problem, if you want, that we are estimating the variance of epsilon, and for whatever reason, we are going to get into a region where epsilon is so small that all the equilibria disappear, and we have a problem here. No, we don't have that problem because we do not estimate the variance of epsilon.
But it must be that the scaling of things is such that
it could be. It could be, yeah. It could be that the parameters become, because everything is divided by sigma of epsilon, the parameters become so large, okay, that it's equivalent to basically have an epsilon variance of epsilon close to 0, and then the equilibria disappear. It could be. That's interesting. That's interesting. Yeah.
So, I mean, effectively, what we are doing is we're treating this as a smoothing parameter.
Pretty much, yeah. Yeah, yeah.
But it also sounds like, as a practitioner, these issues of non-existence of equilibrium, it doesn't show up.
No, they don't show up. Quite the opposite. The problem is a problem of richness of equilibrium. Yeah. Okay, then Newton's method, convenience for convergence, no so convenience because each iteration can be very costly. A spectral radius. Let me just mention it very briefly. I'm not going to present exactly the iteration equation. But basically, these are state-of-the-art methods in computer science to solve system of nonlinear equations. A very high dimension with millions or billions of possible nonlinear equations, okay? And the key nice feature of this method is that they try, and there is a lot of developments in that literature recently, they try to exploit the best things of fixed point iterations and of Newton iteration, okay? What is the best thing of fixed point iteration? That we do not, that is gradient free. It's derivative free. Basically, you have to compute the function phi for every new value of the vector of choice probabilities, but not derivatives at all. Well, the spectral radius method, they are iterative methods where you only at each iteration you have to calculate the phi at the best response at a new vector of choice probabilities. No derivatives at all. And they try to replicate the good properties of the Newton's method in the sense that without using the Jacobian, they have ways of weighting basically the best responses in a way that at the end it has convergence properties that are very similar to the Newton's method, okay? Then they have, then each iteration is very, very easy to implement, and they have much better convergence properties than fixed point iterations. Of course, as you not surprising, the number of these spectral residual method iterations that you need for convergence can be larger than Newton's iteration, of course. Okay? But it hasn't applied both for solution and estimation of these type of models, and I think that this is the good thing is that we can borrow for very well-developed and studied methods in computer science to solve system of nonlinear equations. Okay. Okay, I have here, in fact, one example of the equation. Okay. Identification. And suppose that we have data, typically in I/O, this data comes from data for an industry with multiple geographic markets, okay? Then I'm going to index M, use the index M to index different markets. Each market here, there is no spillovers or equilibrium effects across markets. Each market has an equilibrium, okay? Then what we observe, I'm going to assume most of the time, if not all the time for simplicity, that the researcher observes, has the same information basically as a player in this game. It observes all the common knowledge state variables, X observes the actions, okay? And the only thing that we do not observe as researcher as these private information shocks, okay? Of course, everything that I'm going to present to you here can be extended to models with an observed heterogeneity, especially time invariant market and player and observed heterogeneity. That, of course, is very important. Okay? Then the primitives of the model that we want to estimate are the payoff functions, the discount factors, and the distribution of the state variables. I'm going to use theta to represent the vector of all the structural parameters that parameterize this function. Okay? The identification problem consists of using the data and the restrictions of the model to get either a unique value of theta that explains the data, in the case of point identification, or a set of values of theta that explains the data, in the case of partial identification. Okay? Okay. Then there are different identification problems here in this literature. Okay. First, when we have an observed heterogeneity from the point of view of the researcher that is persistent over time, then we have the well-known problem that if we do not account for this unobserved heterogeneity, then we can spuriously consider dynamics effect. What really is not dynamic effect is just the effect of serially correlated variables. Okay? Other common identification problem is that if there is unobservables that are common across the different players, market and observables, then we may these unobservables are going to affect my behavior, but they will affect also the behavior of other players in the game. Then we may end up, if we do not deal with these unobservables, we may end up interpreting as strategic effects or social interaction effects in a social interaction game, which are only just the effect of an observed heterogeneity. We observe that all the firms tend to be in the same type of markets, most of the firms, and we interpret this, okay, there are positive spillover effects. If my competitors are in this market, I want to be also in this market. When this could be just the result that the markets where we observe most of the firms present are markets that are better according to some unobservables than the markets that do not attract very few firms, okay? Other identification problem is how to distinguish the effect of current profit from forward-looking behavior, from the effect of my expected future profit. Can we identify the degree of myopia of the players? Can we identify these discount factors? Okay? And there is other potential problem, but I'm going to emphasize that this is a problem that makes the estimation much more complicated, but it's never an identification problem, and it's the problem of multiple equilibrium, okay? Yep.
A clarification on the first point. The issue here is that the serial correlation is not perfect. It's like it's going to wane out at some point, and then my current observation of somebody is no longer predictive of how they're going to act in the future. Is that kind of?
No, it's much simpler. What I'm arguing here is much simpler than that. No, is that you observe that firms that have invested in your data, that firms that have invested in research and development in the past, they are more likely to continue investing in research and development now. No, there is a lot of persistence over time in these investment decisions. Okay, and then there are at least two main ways of explaining this persistence over time in players' decisions. One will be there is true causal effect of past investment decisions on today's profit. Because you have invested in the past, you have built some knowledge capital that makes the marginal profit of investing today larger than if you had not invested. There is some form of dynamic complementarity between past investment and today's investment. And this is basically the true causal effect of the past on the present. And there will be some structural parameters in the model that capture this strategic complementarity between the investment decision past and current investment decision. And this is a way of explaining the data, and very interesting in principle. It has economic content. The other natural alternative explanation is no, there is no strategic complementarity, is that firms that have invested in the past and that they invest in the present in research and development are different. Okay? They have more benefits for exogenous reasons and idiosyncratic reasons that other firms that have not invested. Okay? And if we do not account for this unobserved heterogeneity, we are going to interpret all this correlation as the result of this strategic complementarity. And we are going to overestimate this strategic complementarity. Okay? If you are interested in predictions, probably you don't have to care at all about distinguishing between these two. But if you are interested in which are the economics behind this persistence and policies, you can think in a policy that introduces a subsidy to invest in research and development. If the first story is the one that is true, once you have removed this temporary subsidy to invest in research and development, it's going to have long-lasting effects. If all the persistence is because of unobserved heterogeneity, once you remove the subsidy, everybody will come back to the initial investments in research and development, and this policy does not have any long-lasting effect. And distinguishing between the two stories has a lot of economic and policy implications. Okay?
So when you say serially correlated, it's not that the epsilons are necessarily serially correlated in the realizations. It's that if we have an entry-exit kind of model, my competitors will tend to be ones that have had good realizations of epsilons. They will be completely uncorrelated over time.
But they are of a type.
But the selection process is such that they will tend to be positively selected. Is that what you mean by serially?
It's not so much endogenous selection, that of course there may be something like that too, but it's that we have different type of firms, the firms that have low entry costs and the firms that have entry costs, and this could be completely permanent over time. Okay? And then if we do not deal with this permanent and observed heterogeneity, then we will end up with confounding the true dynamics from spurious dynamics, let me say. Okay? Okay? Let me spend a couple of minutes here in the multiple equilibria. Why multiple equilibria is not a problem of identification, okay? Well, the problem of we have a problem of identification where, given the data, there are multiple values of the structural parameters that can generate the same data generating process. That's what non-identification means. Multiple equilibria is the opposite in some sense, or is the reverse of this. Is given our model, a single parameter theta, single value, we have multiple predictions, okay? Then no identification means that from the data to our model, there is a correspondence. Multiple equilibria means that from the model to the data, there is a correspondence. They are very different type of problems, okay? Then one way of dealing with the problem of multiple equilibria when estimating this model, we are going to see many applications say, let's assume that there is only one equilibrium in the data, okay? Despite the model has multiple equilibria, given the true value of the structural parameters, the data generating process has selected one type of equilibrium, or at least one type of equilibrium for a given type of market according to observable variables, okay? Then we are not making that assumption for identification, okay? We are making that assumption because it simplifies very much the estimation of the model, okay? What is the problem of multiple equilibria that can generate problems of identification? Well, suppose that we say, I'm going to relax the problem of a single equilibrium in the data. I'm going to allow each market to select its own equilibrium. But I'm going to assume that according to observable variables, I know the equilibrium that each market chooses. That is, the equilibrium selection only depends on observables, and I know the way that this is done. Again, multiple equilibria will not generate any identification problem. Where multiple equilibria is associated with identification problems? When we say that there is multiple equilibrium in the data, or there may be multiple equilibrium in the data, and the way that markets have selected equilibria is something that I don't know. Well, the problem then is not multiplicity equilibria. The problem is an observed heterogeneity. That is, each market is of an unobserved type that makes it to select one equilibrium or another. And of course, an observed heterogeneity creates identification problems, but not because multiplicity of equilibria. We will have the same identification problem associated with an observed heterogeneity in the payoff functions, okay? Okay, then a set of assumptions that are very common and that give us, help us to get equilibrium uniqueness. No common knowledge state variables, no unobserved heterogeneity, single equilibrium in the data, additive unobservables, known distribution of the unobservables, and the conditional independent assumptions. These are very common assumptions. They are convenient for computation, but they are identifying assumptions. They play a role in the identification of this model, okay? Under these conditions, we can use Hodge-Miller inversion theorem to get a positive identification result. Suppose under this condition, what we have is that the probability distribution of the actions of player I conditional on the observable state variable is just an expectation that we can estimate from the data. Then these choice probabilities are identified. And under Hodge-Miller inversion theorem says that given choice probabilities, we can recover conditional choice value functions. And we have identification of this, okay? Unfortunately, this is not enough. Once we have identified this is not enough to identify the primitives of the model, okay? And in principle, that doesn't give us identification of the discount factor. There is a normalization that is not innocuous in this type of model, and that plays a role. And also, very importantly, notice that what we are identifying is these conditional choice value functions integrated over the distribution of the actions of my competitor, okay? But we are not recovering a utility function or a value function that depends on my action and the actions of my competitor, okay? That will require additional identifying restrictions, okay? Then some common additional restrictions that are going to help us to get identification. Well, the typical normalization, that there is one of the payoffs for one of the choice alternative is normalized to 0. Typically, if we do not have other type of restrictions that I'm going to consider later, we assume that we know the discount factor. And finally, in order to identify strategic interactions, how the actions of my competitor affect my payoff, we need some kind of exclusion restriction, okay? This is basically Mansky's reflection problem, trying to identify the actions of my competitors on my behavior, okay? Then the typical type of exclusion restriction is that the vector of state variables contain firm-specific state variables. For instance, in the model of investment in quality, every firm has his own stock of quality, okay? That is going to affect his profit. Then what is the exclusion restriction? The exclusion restriction is that my profit function, once I control or I condition on the actions of my competitors, on how they have decided to invest in, do not depend on the previous stock of quality of my competitors. The previous stock of quality of my competitors has an effect, because it's an state variable, has an effect on the behavior, on the investment decision of my competitor, but does not have a direct effect on my profit function, okay? And this is an exclusion restriction that generates variation in the action of my competitor, but does not have a direct effect on my profit. And this type of exclusion restriction typically appears in most of these dynamic games. Other example is a model of entry and exit. My profit depends on how many competitors I'm competing with, but does not depend directly on whether my competitors were in the market or not at previous period. But whether a competitor was in the market or not at previous period has an effect on the choice probability of the competitor of being in the market today, okay? And it's the expected behavior would affect my profit, but does not have a direct effect, okay? Okay, then under all these restrictions, we have non-parametric identification of all the objects in this model. And that was established in a proposition by Pessendorfer and Smith-Henkler, okay? Now, we can relax most of these assumptions. We can allow for serial correlation and unobservables. We can allow for multiple equilibrium in the data. We can relax, at least in terms of counterfactual experiments, normalizations of the payoffs. We can identify under other type of exclusion restrictions the discount factors. We can allow for non-additive unobservables. We can also allow, there is work on non-distribution of the unobservables, and there is even work on non-equilibrium beliefs, okay? And there has been a lot of developments in recent years on extending basically the identification of this type of models to relax almost each of the assumptions. Perhaps not all of them at the same time, okay? Okay, estimation. Let me go through two types of estimation methods, full solution methods and two-step methods. How I'm doing in terms of time? How much? 20 minutes, okay. Then let me start with maximum likelihood estimation with unique equilibrium, okay? And in particular, nested fixed point with unique equilibrium. this has been perhaps the author that, in the context of dynamic games in I/O, that has used this framework more extensively is Mitsuru Igami, in a series of papers on innovation, dynamic games of innovation. Of course, having a unique equilibrium in this type of models is very convenient, both for estimation and especially for counterfactuals. Once we have estimated our model and we do counterfactuals, if we have a unique equilibrium for every possible value of the structural parameters, counterfactuals are going to be very straightforward to implement, similar to counterfactual in single-agent models. Now, this requires assumption, okay? Only under very substantial restrictions on the dynamic game, we can have equilibrium uniqueness, okay? The ones that have been most commonly imposed in this literature to get equilibrium uniqueness are the following. First, we have a finite horizon, okay? And second, at every period t, firms choose sequentially. It is as if within each period we had several subperiods. First, firm I chooses investment, first 1 chooses investment, then firm 2 chooses investment, firm 3 chooses investment, and so on, okay? And we should determine a sequence of moves within each period, okay? That doesn't come without loss of generality, and it has implications on the predictions of the model. Of course, we know all that in many models, there are first mover advantages, okay? Then under these restrictions, it's trivial to show that we have always a unique equilibrium, okay? Basically by using backwards inductions across periods and backwards induction within period, okay? It's straightforward to show that we have a unique Markov perfect equilibrium, okay? And then we have, given every value of the structural parameters, we have a well-defined likelihood function, and we can apply the nested fixed point algorithm as usual, okay? We start with some initial guess of theta, and at each iteration, we apply, for instance, BHHH. These scores depend on the derivative of the equilibrium probability with respect to theta, but at each iteration, we solve for the unique equilibrium of this model by backwards induction, and we take the derivative of the equilibrium choice probabilities. And substantially nothing really different to nested fixed point in a single agent dynamic programming problem, okay? Okay, what about multiple equilibria, okay? Now I'm going to talk about the nested fixed point, 2 different ways of implementing the maximum likelihood estimator, using the nested fixed point and using MPEG, okay? And using the nested fixed point, okay, what we need, what is key to implement the nested fixed point in models with multiple equilibria is that we need a powerful algorithm that for every trial value of the vector of structural parameters theta, we can calculate all the equilibria of the model. And that's, for instance, the case of the recursive lexicographic search algorithm by Fedor, John, and Bertel in a particular class of dynamic models, okay? Then this algorithm in a particular type of dynamic models can give us all the possible equilibria that the model has for a particular value of theta, okay? Let me mention that the paper by Doroselsky and Satterwhite in theoretical economics shows that within this class of models, generically, the set of equilibria is discrete and finite, okay? And we know that we have only a finite, for every value of theta, we have only a finite set of equilibria, okay? Then let me use tau to index equilibria, okay? Then calligraphic P represents the set of equilibria that we have for a value of the structural parameters. And each of these p taus represent one equilibrium vector of choice probabilities, okay? Then here, the maximum likelihood estimator can be defined as a value of theta and tau that maximize this likelihood function. Where this likelihood function we have that depends on theta, but depends, given theta, depends on the type of equilibria that we have. Yep. Very good question. Okay. It's a type of equilibria basically where the Jacobian matrix of the equilibrium mapping, this phi mapping, is non-singular. Okay. And the problem, okay, what happens if that matrix is singular? The problem is that then we can have basically infinite type of equilibrium for some particular values of theta. Okay, there is a continuity of equilibria. Okay, then what they saw is that these non-regular equilibria, there may be many. Okay, but the set of regular equilibria is always finite. Okay. And non-regular equilibrium, they are a strange animal, okay? And I think that is reasonable to focus on regular equilibrium, okay? This is genetic, that's what they mean by genetically, okay? For every value of theta, there is a finite set of regular equilibria, and, but there may be many non-regular equilibria. Infinite non-regular equilibria. Okay, then how do we implement this nested fixed point algorithm with multiple equilibria? It's a very straightforward extension of the standard nested fixed point. Okay? We start with an initial guess of the vector of structural parameters, and then at each inner iteration, the inner loop of the nested fixed component algorithm, it has now two parts. Okay? The first part is the solution, where given at iteration n, given theta n, we obtain the set of, we use Fedor's and Bertel's algorithm to calculate all the equilibria that the model has for this vector of structural parameters. Then we get the set of equilibria calligraphic P, okay? And now, given that we have calligraphic P, taking as given theta n, okay, we choose the likelihood. Notice that we have multiple likelihood functions, one for each tau, for each type of equilibria. We choose the value of tau that maximizes in tau the likelihood function, okay? Then given that particular value of tau, then we apply BHHH, okay? As usual, we obtain the scores, and we obtain then a new value of theta. And given the new value of theta, we proceed again in the same way up to convergence, okay? And quite similar to the standard nested fixed point algorithm, but at each iteration, we need to maximize with respect to the type of equilibria that we have, okay? MPEG is an alternative way to define and to implement the same thing, that is the maximum likelihood estimator, okay? And it's based on a different version of the likelihood function. What we can define, the pseudo likelihood, or the extended, they call it, if I remember well, the extended likelihood function, okay? What is the extended likelihood function? Well, in the likelihood function that I have presented before, is a function of theta only, okay, of the structural parameters. But given theta, we have multiple equilibria. Then instead of using equilibrium probabilities, what we could consider here is a likelihood function where we think basically that we were trying to estimate the structural parameters and first beliefs about the behavior of the competitors, okay? Then given a player belief about the choice probabilities of my competitor, I have a best response function. I know the choice probabilities of my competitor, and I know basically I have a best response function, okay? What is a correspondence is the equilibrium correspondence, but the best response are all these functions in this model, okay? Then taking as given my beliefs about how the competitors will behave, this is my best response choice probabilities. These are the logit probabilities that I have written before, where choice probabilities of my competitor is given. Okay? Then this is a well-defined likelihood function. Okay? But now the objects, basically the set of parameters in the likelihood function has increased very substantially. It includes theta and it includes p. Okay? Then the maximum likelihood estimator, the same estimator that I have defined before in terms of different equilibrium types, okay? Exactly the same object can be defined according to this expression, okay? Is the value of theta and p. Before, remember that we were maximizing with respect to theta and the type of equilibrium tau. Here we are maximizing with respect to theta and p, okay? This pseudo-likelihood function subject to this equilibrium constraint, subject to given theta, the vector of beliefs, if you want, the vector of choice probability should be in equilibrium, okay? Typically, if we had a unique equilibrium, what we will do is we have this equilibrium mapping, we solve it, we obtain the vector of choice probabilities p of theta, and we plug it in q theta p, and then we have a likelihood function that depends only on theta. We cannot do this because given theta, there are multiple p's that solve this system of equilibrium equations. And that's why what we do is maximize the pseudo-likelihood function under constraints. Okay? But this is a well-defined constraint maximum likelihood estimator, and the maximum likelihood estimator has the same properties, good properties, as any maximum likelihood estimator. Okay? Now, this maximum likelihood estimator is defined as a value of theta, p, and the vector of Lagrange multipliers that solve this Lagrange function. Okay? As you can see, now the object of the maximization is homologous. Okay? And the set of Lagrange equation involves basically this particular object that is the Jacobian matrix of phi that needs to be calculated repeatedly, and it's a very complicated object. And this is very complicated to implement. Okay? Okay, two-step methods. For concreteness, let me suppose that the payoff function has this particular multiplicative structure in terms of the structural parameters. Okay? Then, under this structure, it's possible to show that given the choice probabilities of a player, we can write the conditional choice value function, given p, as basically this linear expression, okay? Where h tilde p is no more than the present value of the h, okay, vectors that we will visit in the future if players behave according to the vector of choice probabilities p. And this EP is basically the expected value of future epsilons that we will get if individuals behave according to the choice probabilities in P. And here I have assumed logit errors. We will have a different expression without logit errors. Okay? But we can calculate these present values either by solving a valuation operator that basically is equivalent to inverting a matrix with the dimension of the state space, or if you prefer, we can do it by forward simulation, okay? Given that we know the vector of choice probabilities and the transition probabilities of the state variables, I can simulate actions and state variables, obtain paths of simulations, and use them to approximate these expectations, okay? But given P, notice that these objects do not depend explicitly on the structural parameters. The given choice probabilities, I can calculate these objects. These objects are known to the researcher, okay? Then what are a two-step estimation method is just, okay, let me say first, then given P, I can calculate these basically best response functions in this way, okay? And then I can put these best responses in my pseudo-likelihood function. And basically, this is like the likelihood function or the pseudo likelihood function with these choice probabilities will be the likelihood function of a standard, a static, if you want, model, discrete choice model. Okay, that is, I have obtained already the present values here, and now we need only to maximize with respect to theta. Okay, and that's the nature of the two-step estimator. Basically, we start with an initial non-parametric estimator of p's. Given this non-parametric estimator, we calculate these present values, we plug them here, and we estimate theta using a standard maximum likelihood estimator of a multinomial logic model. As simple as that. Okay? This can be done with forward simulation or without forward simulation. This is, of course, computationally much simpler than the previous method, which is an important limitation of this approach is that, well, typically the initial estimation, non-parametric estimator of the choice probabilities can be very noisy. Okay? We have a few thousand of markets or a few thousands of observations to estimate choice probabilities that might be choice probabilities in millions or billions of possible states. And we have very few observations to estimate these choice probabilities that can be very noisy. Okay? Then one way to try to improve the finite sample properties of this estimator is by imposing recursively the equilibrium restrictions. Basically, by applying this algorithm recursively. Once we have obtained estimates of theta, now we know that these are the best response functions. Then given our initial estimate of p and my estimator of theta, now I can use this expression to obtain a new estimate of the choice probabilities. And then I can use this new estimate of the choice probabilities that are using now more structure of the model, some best response condition and some parametric conditions in the model, to construct new present values here and here. And then I can do again the same thing. Okay? And there are several papers that showing that this iteration reduce the finite sample bias and improve the finite sample properties of this estimate. And in principle, we could iterate in this way up to convergence. Unfortunately, convergence is not guaranteed. And there are good examples showing that there are failures to converge. Okay? Okay. And that's it.